Hello and welcome to our video on simple harmonic motion. Now you may be wondering to yourself, what is simple harmonic motion? Basically, this refers to the motion involving a body that oscillates. Okay, before we do anything, let's look at an example of simple harmonic motion. And the simplest example would be a simple pendulum. And we'll be looking at the motion of this pendulum. So this A would be its positive side going towards its negative side C. At A, it would be its maximum positive displacement. At B, it would be zero displacement or its equilibrium position or rest. And C would be its maximum negative displacement. We can represent this in a graph, so this would be A, its maximum positive displacement. This would be B, its maximum zero displacement or rest or equilibrium position, and this would be C, its maximum negative displacement, and this would be the rest of the cycle going back. Before we looked at the motion of the pendulum in terms of displacement, now let's look at the motion of the pendulum in terms of velocity, or V. I have a video arranged to help explain this. So this is a simple pendulum. As you can see, as it's going towards the center, the velocity is increasing, and as it's going away from center or equilibrium position, the velocity is decreasing. And if you did mechanics, you would know that at the highest displacement position, the velocity would equal zero. So over here, A would be its highest maximum displacement position, and at A, velocity would equal zero. And as we saw in the video, as you're going down towards the equilibrium position, so like that, as you're going down towards the equilibrium position, the velocity increases. So from A to B, velocity is increasing. And at B, this would be its maximum velocity, so V max. From B to C, it's moving away from its equilibrium position, so the velocity will be decreasing. So B to C, velocity decreasing. And C would have zero velocity again because it's a maximum displacement position again. Velocity is equal to zero. And this is for the motion of the pendulum from A to C. From C to A, it would be the exact same but the opposite. So at C, zero velocity again. From C to B, velocity would be increasing. This would be in the negative direction, by the way, the velocity of A to B, and the velocity of B to C, C to B would be increasing in positive direction. At B would be max velocity again, and from B to A, velocity would decrease. And at A would be its velocity equals zero. Now let's put this information into a graph. If I draw the axes here, that's too far away. On here would do. Use a different color. Velocity time. That would be positive, and that would be negative. So, as you can see, at A velocity is zero, and from A to B, the velocity is increasing to its maximum, which is B. And from B to C, the velocity is decreasing to C, which is zero again. and that's for the first half of the cycle. And for the second half, where it goes, that's from A to C, and the next is going to be from C to A. As C velocity is 0, as we can see from C to B, velocity is increasing towards its maximum, and at B is its maximum, and from B to A it's decreasing back to 0, which is A. So it would look something like this if it was drawing a bit neatly. Since acceleration is given by the gradient of a velocity time graph, therefore the gradient of the last graph will give the acceleration of the pendulum. By looking at this, the gradient of the velocity time is negative at first, becoming 0 in quarter of a cycle, so here, then reaching its maximum positive value here in half a cycle. So if I were to draw this as an acceleration time graph, you'll see that acceleration would be here, time would be here. It would look something like that. Was negative at first, becoming 0 in quarter of a cycle, then reaching its maximum positive in half a cycle. Okay, whenever if we compare this with a displacement time graph, we can see that whenever the displacement is positive, acceleration is negative. And by looking at these graphs, we can work out that acceleration is proportional to displacement because the maximum values are at the same time. So that means acceleration is proportional to displacement. Okay, now let's try and define simple harmonic motion. By looking at these graphs, we know that acceleration is proportional to displacement, and we can work out that acceleration is towards the equilibrium position. This is because when we know that the velocity increases as it's going towards the equilibrium position, that means it's accelerating. We can write this A is proportional to x displacement as A is equal to minus cx, where c is a constant and it's negative because A is in the opposite direction to displacement. We normally square the constant because we want to keep the negative sign to show that acceleration is in the opposite direction to displacement, and the constant is normally 2 pi f, and we square it, as I said, x, and 2 pi f is the angular velocity, or omega. Let me just write that in another colour as a reference. Omega is equal to 2 pi f. So the final equation we get is this: A is equal to minus 2 pi f squared x, or we could rewrite this as A is equal to minus omega squared